Good evening, everybody. This evening, we're welcoming Ernst de Mooij, who's a lecturer at the Queen's University Belfast. He obtained his PhD from Leiden University, after which he became a postdoctoral researcher at the University of Toronto. Subsequently, he moved to Queen's University Belfast as the Michael West Fellow. Following on from that, he was an assistant professor for 3 years at Dublin City University. And tonight he's in Swinton and Mexborough Astronomical Society for the very first time. So please can everybody put their hands up and give him a Mexborough and Swinton welcome. Thank you.
All right, thanks. Nice to see you all and give this opportunity to give a talk. So let's see, I'm sharing my screen, hopefully. So yeah, so I'm Ernst de Mooij. I'm a lecturer at Queen's University Belfast in the Astrophysics Research Center. And today I'm going to tell you a little bit about how we can investigate the atmospheres of planets outside of the solar system. But before I go there, I always like to start with a quiz. So this will be a little bit of interaction if it works. So feel free to either, when I ask a question, unmute or type it in the chat. And I always like to start with a question here. Can anyone tell me roughly what time of day this was taken?
Evening.
Okay, so evening.
2 o'clock in the morning.
Yep, it's basically somewhere in the middle of the night. So this is on the island of La Palma, and you can see the stars here. And if you look carefully, you can see a few big telescopes. The William Herschel telescope over here, which is a 4-meter telescope. We have the Liverpool telescope down here. And this is called the Mercator telescope, and this is taken from the Isaac Newton telescope looking at out. And typically when you're observing exoplanets, because they all orbit bright stars, you get to the darkest sites in the world on nights with full moon, like here. And as you can see, that gives you a very nice blue sky if exposed long enough. I need to pause here if this works. Oh, it doesn't want to. Why is it not pausing? Okay, there it is. So I'm going to ask you one more question. Can anyone recognize any of the constellations here?
No.
I'll give a hint. This here is actually not a star. It's Mars. And the constellation is slightly tilted, so it's sort of on a diagonal line. And yep, I see a correct answer there in the chat. It is Leo. It's here you can see sort of the front end of Leo, and then Mars is over here. So as I said, I'm going to tell you a little bit about how we can investigate the atmospheres of alien worlds. And to do that, I'll go from how can we actually find planets around other stars to then also even look at comets around other stars. And the goal is basically to show you how we can go from observation in the solar system, like here during the transit of Venus, where you can see a sliver here where light from the sun is filtering through the atmosphere towards Earth, to studying exoplanets, like this very high quality artist impression I made of a planet passing behind the star, or a slightly higher quality one where we can see the same light from the star filtering through the atmosphere on our way to Earth. But first, we need to find these planets, right? So up to 25 years ago, we had no clue whether there were planets outside of our solar system. We knew of the planets in our solar system, but nothing outside of it. And if we go a bit further back in time, basically for thousands of years, humanity didn't find any new planets even within our solar system. We didn't have to complete census. That changed in the 18th century when William Herschel published this paper called Account of a Comet, which I always find an interesting title, which actually turned out to be Uranus, right? So I always find it interesting that William Herschel confused a planet with a comet, but then again, he wasn't pre-expecting to find more planets in our solar system. And so to place again into context, we know of our solar system with 8 planets, 4 rocky planets that are inside, right? So they're to the left here, they're closest to the sun, and then 4 gas and ice giants on the outsides. And so this is actually important when we start looking at other systems with planets, because when we started looking, we were thinking we might find something like the solar system. So we might find a planet like Jupiter, which is in over 10-year orbit, right? So it's takes a long time, so it would require quite a lot of observations. And we will see that that's actually not the case when we look at other planetary systems. So how do we actually find the exoplanets? Well, let's start with outlining the problem. Because in the solar system, we can put our telescopes outside, we can point them, we can track points of light on the sky that move with respect to the stars, and those are the planets. But if we look at it from further away, we need to work out how bright is the planet compared to the sun. And so on the y-axis here, I show the relative brightness compared to the sun. So how many times fainter is the planet than the sun? On a logarithmic scale. So each big step up is a factor of 10 brighter. And down here is 1 in 100 million. Down here at the bottom is 1 in 100 billion. So the planets are hundreds of millions down to hundreds of billions of times fainter than the sun, right? So they're really faint. And also, if we look at the best two planets, right, to look at would be Venus, because it's fairly bright, and Jupiter, which is here. They actually orbit relatively close to their star. So if we're looking from Earth, we're trying to distinguish a very faint dot of light right next to the bright star. So that's challenging. And so this problem has been likened to finding a firefly next to a lighthouse. And I should correct this image because this looks like it's easy. This is more like how we are looking at it, right? So it's hard to see these planets, or in this case, the firefly. It just gets outshone by its star. Nevertheless, with perseverance, very good telescopes and specialist instruments, we have managed to image a few planets directly. So what we do is we use something called the coronagraph to block the light from the stars. So that's why there's a dark hole here in the center. So the star is here, but that's blocked by the instrument. And then we can see the planets around here. In this case, there's 4 planets for HR 8799. I mean, these names are, for astronomers, very useful, but not always very interesting to hear. And down here, we have Beta Pictoris b. Again, the star is hidden here behind the coronagraph mask. And the planet is seen here on the side. And why can we see these particular planets? Well, that is because these are very young planets. So when planets form, they collapse from a cloud of dust and gas. And as that basically collapses, it releases energy and starts to glow. So basically, when planets are young, they're very hot and they emit a lot of light, especially in the infrared. And these specialized instruments were looking in the infrared at this glow left over from when they're formed, much less than 100 million years ago. And what's interesting, we've now been observing these planets for quite a long time. And I'm going to rotate this figure here a little bit to set the context, because over time, we've managed to actually observe them over years, and we can see them orbit their star. So what we see here is the planets orbiting their star over the course of about 10 years, right? So we can see them actually move around their star. We can start following them and learn a bit about them. And so I find this actually amazing that we can get these images and learn a bit more about how they move and actually see them move as well. But in most cases, these planets, if you look at the solar system, they're just too faint, they're hidden behind the glare. And with the current generation of telescopes, we're unable to actually detect these planets. So we need to look for other methods. And one of the most interesting methods is actually look for an indirect effect called the stellar wobble. So if we have a planet orbiting a star, that's not quite true just by saying that the planet goes around the star. Actually, what happens is that the planet and the star go around a common center of mass, right? So they orbit sort of a midpoint based on the masses. Of course, we don't see the orbits. And so we see the star making a small circle because it's much more massive than the planet, and the planet making a much bigger orbit. And so in reality, what we see is something like this, of course, because the planet is too faint. We see the star wobble around this center of mass, and we can measure that wobble to determine the mass of the planet and basically show, hey, there's a planet here, and this is roughly what its mass is. The problem is these movements are very small. So this is a very exaggerated movie. This is a model of what it would look like if we were able to observe the solar system from 1970 up to about 2020, 2030, from basically the pole of the solar system. So looking straight down on the planetary orbits, and we see the sun described in orbit. So it starts here in 1970, and it wobbles around with time. And the majority of this wobble is due to the planets Jupiter and Saturn, which are the most massive planets in our solar system and also in quite wide orbit, so they have quite a large effect. And this looks quite nice, right? We can see this wobble, but what does it look like if we compare it to the size of the sun? Well, that's roughly the size of the sun on the scale. So on this scale, the planet or the sun moves by maybe twice its diameter, 3 times its diameter. So it's a tiny signal and very hard to find and measure accurately. And so at the moment, not many planets have been discovered by this technique, by measuring the position of the star. But we have the Gaia satellite out there, and hopefully soon it will start publishing the planets discovered by this wobble that it is able to measure. But it just takes a lot of data and data analysis to find, so that's why we haven't got anything yet. So is there another way to measure this wobble? Well, if the star is moving around on these orbits, it also means it has a velocity. So if we can measure that velocity, that would be great. Well, and we can do that by using a technique called spectroscopy. And what we do is basically separate the light out in its different wavelengths, the different colors, going from short wavelengths here in violet and then blue, all the way to red on the right. And of course, it then goes on the infrared even further on. And we then take advantage of a special property of atoms and molecules as well, is that they only will emit light at very specific wavelengths. So hydrogen emits light in the red, called hydrogen alpha. And that's around 656 nanometers. So it's quite dark red to your eyes. It then emits at about 486.1 nanometers, etc., and very specific wavelengths. While iron has many, many more lines. So you can see them sort of here highlighted. So these are not all the lines. And when they look very broad, that means there's just a whole load of lines together. But we know exactly from laboratory measurements where these lines are. So we know exactly what their wavelength is. Just to show you what it looks like if we take a spectrum of a real object. This is a spectrum of the sun. I've taken actually with my own spectrograph, which hopefully I get to use for a demonstration later on. And you see all these wiggles here. These are not just noise or anything else. These are real lines from atoms and ions in the solar atmosphere. I just want to point a few out. So we have lines of hydrogen here that are marked here. So this is H beta, if you're familiar with that, if you've heard of that, and this is H gamma. And then another, or gamma. And then another important line here is magnesium. It's also a group of lines that are quite strong in the sun. And so we know exactly where these positions are. So if we can measure how much where they are in other stars, we can learn something else because we can take advantage of the Doppler shift. So here again, I'm just simplifying it again to just look at hydrogen. We have a spectrum of a star. And then as the star changes its velocity towards us and away from us, effectively it causes the wavelength of the light that we see to change. So what we see is that over time, these lines move back and forth due to the Doppler shift and the velocity of the star. This, what I show here, is quite exaggerated because in reality, these velocities are a bit smaller. The sun's velocity due to the Earth is 400 meters per hour. So basically 10 centimeters per second. So roughly, if you can see my video, something that moves at about this speed. And that is an object more than 1 million kilometers across moving at, well, a very slow crawl. Jupiter, being the most massive planet in our solar system, actually causes the largest change of about 40 kilometers per hour, which is roughly the speed you drive in a city, right? When you're driving at, it's still very slow, about 10 meters per second, if you wanted to meters per second. So in reality, it looks more like this. So let me start the movie. So I hope you can see this movement. It's tiny, right? The fractional changes are less than 1 part in 300 million if we look at the Earth, right? So these are tiny, tiny signals that we need to measure very, very accurately. Nevertheless, people have started doing that. And these two people here, Michel Mayor and Didier Queloz, used the instrument here called Elodie on the 1.8 meter telescope in the Observatoire de Haute-Provence to observe several stars, including a star called 51 Pegasi. And what they found was that periodically the star appears to move away from us. So time is here on the x-axis. And on the y-axis, I show basically the color of the light. Blue is the star coming towards us. Red is the star moving away from us. So what we see is the star moving away from us, then coming towards us again, then moving away from us again, and coming towards us again, etc., etc. As if there's an object pulling it, the star basically in an orbit, and so the star is moving back and forth towards us. What was interesting was that when they looked at actually the velocities, the star is moving at about 60 meters per second, which is roughly probably the speed of a sort of light aircraft. So not a big jet, but a light aircraft, or maybe a jet on a just about to land, right? So about 200 kilometers per hour. So this was much faster than anything we'd seen in the solar system, right? We would expect, if you look at Jupiter, we would expect maybe 10 meters per second. We found something that moves 6 times quicker. But what was more interesting is that this planet completes a single orbit. So 1 year on the planet is just 4.2 days on Earth. So this planet, in the time it takes the Earth to go around the sun once, goes around the sun more than, or about 90 times, right? So this is really, really a short period planet. This actually won Michel Mayor and Didier Queloz the Nobel Prize, and this is actually Didier Queloz's actual Nobel medal that he received for the discovery of the first planet around a star like our sun. But I mentioned this 4.2 days, right? That's really, really short. So let's compare that to the solar system. So here in green, I show this planet 51 Pegasi b going around its star and compare it to Mercury here and Venus here. And so you can see how close 51 Pegasi b is to its star. And I should say the star is here not to scale, and also the planets are not to scale in size, because that would, of course, make Mercury and Venus absolutely invisible. And even 51 Pegasi b, which is roughly probably the size of Jupiter, would still be just a single dot. But this is extreme. And this is actually one thing that's very important when we start looking at the atmospheres, is that because this planet is so close to the star, it receives an immense amount of stellar radiation, so an immense amount of light, which means its day-side temperature gets quite high, well over 1,000 degrees in the case of 51 Pegasi. And we found planets that go up to well over 4,000 degrees as well, which means they actually are glowing red hot. And that makes it easier, not easy, but easier to find their atmospheres. Of course, 51 Pegasi was just a start. When we start looking more, we found planets like this. This is an artist impression of Proxima Centauri b. And I should always caution that what you see in the press is typically very nice images like this, where some artist went and sort of imagined what the planet could look like. What actually astronomers found when they looked at the data is this. So we see the time here on the x-axis in days, going from 0 to about 11 days here on the right. And then the velocity of the star on the y-axis. And this here is 1 meter per second. So this is about 1.5 meters per second. So the star is moving at about 1.5 meters per second, which is roughly walking pace. So if you're going out for a walk, you might actually be going quicker than this particular star is. But nevertheless, we managed to measure it and detect the planet. This method is not without its challenges. So one particular example, and you may have heard about this about 8 years ago, the announcement of the discovery of a planet around Alpha Centauri b, one of the 2 stars that make up Alpha Centauri, and that later was retracted. So just like the Sun, Alpha Centauri actually has occasional star spots and other features like plage and other things. And so what you see on the Sun is if you have star spots, you see these dark dots, and then around them there's typically bright regions called plage or faculae, which basically affect the spectrum of the star. And so over time, so this is about a time span of 1400 days, so about 4 years. What people noticed is that when they started observing as very low activity, very quiet star, basically a bit like the Sun looks during its minimum, right? There's not much going on. And so it looked like an ideal star to observe, but over time, this activity went up until around this period where they have a zoom in, you can actually see this activity vary on a time scale of about 30 days. And this is because effectively the star spots with their faculae and everything around that rotate in and out of view. So we see the star spot here, or the active region on the front of the star here, and then here the active region is on the other side, so we don't see it. Unfortunately, this activity causes the star to appear to wobble as well, which is not due to a planet. It's just the fact that the way the brightness across the star is distributed, the star appears to wobble. So that's shown in this graph, where basically there's nothing visible here at the start when there was very little activity. But then when you go later on, you can see these wobbles in the velocity, and that's purely the star moving back, or basically changing its activity, changing the amount of spots on the surface. And they claimed that they had found a planet, so they accounted for the stellar wobble, and they claimed to have found a planet. But what they also, what went wrong was that they didn't observe the star continuously or as often as they might have wanted to, and that those two effects combined create this spurious signal in the data that looks like there's a planet, but actually turns out to be nothing that really exists. So to overcome this, we are embarking on new projects, and one of that is called the Terror Hunting Experiment, which will be using a state-of-the-art instrument that's currently under construction called HARPS-3, which will be based at the Isaac Newton telescope on La Palma. So that's the telescope you see here. It's a 2.5 meter telescope with based on an equatorial mount. And at the bottom, what they'll do is they'll make a thing where they can plug in a fiber that then goes to the spectrograph, which will be located somewhere in a very stabilized environment, because any vibration, any temperature change could affect the results. And the thing is that this HARPS-3 instrument will be observing about 40 or 50 stars in the night sky every single night, or as often as it can, not quite every single night, but as often as it can, to avoid that all those problems that we've seen with Alpha Centauri b that may really result in spurious data. But even then, this radio velocity method, if we can get it to work properly, right, we get the signal to noise we know we can correct for the stellar activity, has one final problem. And that is that we don't know the orbit in which the star or the planet is orbiting the star. So we can be looking straight down on the system. So we see the star here, the planet here, and as the planet goes around and the star is going around on a nice orbit, it's always on the plane of the sky. So we don't see the star coming towards us or moving away from us. So if we measure the velocity, we just find a straight line here as if there's no signal at all. But of course, we can tilt that orbit instead of being face on, being slightly tilted. And as we tilt it more and more, the signal becomes stronger and stronger. But this amplitude here, so that basically how large that wobble is also a measure of the mass. And as long as we're not able to disentangle whether the orbit is just tilted a bit or the planet's more massive, we can't quite get the true mass of the planet. So any mass we get from this technique is always a lower limit. Except in this particular case shown here on the right, where the orbit is aligned in such a way that it exactly is the stars only moving in and out of the line of sight. If we can do that, we can get the true measurement of the mass. But if we have that, we actually get another thing, right? We see this orbit being aligned here, and we get something that is known as a transit. So now I want to try a demonstration. Let me switch over to the correct instrument here. So what I've done in the other room, of course, there it goes. And let me make this larger. I've set up a big light bulb with a rotating stage. And I'm showing the brightness here on the left. So this is how bright the measurement the camera detects. And it's fluctuating a bit because unfortunately the sun is right on the side of this room where it is. So, and there's a bit of cloud, so that fluctuates a little bit. But as I now start moving the planet, we can see that the planet moves in front of the star, and we see this dip here, right, where it dips down because the planet is blocking part of the light from the star. And as it then continues along its orbit, the star recovers, actually gets a little bit brighter in this case because of the light from the sun. But we can see this dip in light, and as the planet would go around its orbit, you would see this dip periodically happen. So basically every orbit it will dip once because of this. So let me just go back here again. And this dip is what's known as a transit. And just to show you here, I have a simple movie just to show a little bit cleaner. So we have the planet blocking part of the light of the star. And then it continues, as it moves away, again, the star recovers to its original brightness. And what's interesting is because you have basically a circle here, which is the star, and you block it with another circle, this size here of the amount of light being blocked is directly related to the area of the two circles, or basically to the radii of the planet compared to the radius of the star. So from this transit, we immediately get the ratio of the sizes between the two. So let's do a simple quiz here. I have here a star, which basically represents our sun. And we're pretending we're looking from a distant star at the sun, and we're looking at the transit of, we're trying to find the transit of Earth. So does anyone think this is the Earth shadow if we look at it from afar? No, too big. That is correct. So let's move on further. Do you think this is the size? Okay, I get a lot of no's. That's correct. This is about Jupiter, which blocks about 1% of the sun if we're looking at from a large distance. To go to the Earth, we need to go to this size. This is the Earth to scale in front of the sun. If you have trouble spotting it, it's in the square there, and it blocks less than 1% of the light from the sun. So we're looking at tiny variations, which are very hard to find. Right? So nevertheless, we're starting to succeed to find planets like our Earth, although that's hard to do from the surface of the Earth ourselves. Right? But the instrument we're using can be quite simple. So these are just a few examples here. This is called Super WASP here on the left. It uses 8 basically photo camera lenses with good cameras behind them, but otherwise these are just Canon lenses they use to observe a large patch of the sky, monitor a lot of stars at the same time, and try to search for these dips. Here on the right is something called HAT. And again, they're using standard camera lenses, in this case, only 2, to observe large areas of the sky and find these dips in the light for transits. There is a problem, and that's that we're looking for the Earth's atmosphere. So here I have a simple diagram. We have 2 stars here, and I show the amount of light here on the y-axis as a function of time for these 2 stars. And I'm telling you, one of these stars has a planet. Can anyone spot the planet? So do you think it's on the left or on the right? I see left. Okay. Yes, it is on the left. And if you compare the 2 light curves, you can basically, if I draw a line here, right? So it's sort of going like that, and draw that same line here. There's a bit of a wiggle there. You can see that there's a bit of a dip here, and I'll just shade it where the light's a little bit lower. So what we do is we use the light from the other star and divide that into the star which has a planet, and now we can see the transit. So we can see this transit going down. It's about 2.5% in this case, so it's quite a large transit. But we can now nicely see this planet in front of a star. Of course, if we were outside the atmosphere, we wouldn't have this issue, and that's, for instance, why we have the Kepler satellite, which observed a field in near Cygnus for continuously for several years. So this is sort of an animation to show you where it looked. So it was looking at quite a large area on the sky near Cygnus, and it was continuously monitoring and measuring the brightness of more than 100,000 stars to look for these transiting planets, to look for these small dips in light. And because it was above the Earth's atmosphere, it was actually on a trailing Earth orbit, so basically well away from the Earth, it was able to observe continuously and didn't have that much issue with, for instance, systematic effects that could mimic transits or hide transits. And so with this satellite, we found really fun systems like Kepler-11 here, which doesn't just have 2 planets within Venus orbit, but has 1, 2, 3, 4, 5, 6 planets, right? Imagine anything out to Saturn squashed into something that's only marginally larger in this orbit of Mercury. So these are really weird systems when we compare them to Earth. And this is one of the reasons we want to study these systems, and also try to understand what kind of planets are we looking at to understand their atmospheres, so we can learn more about how they formed and also what that tells us about the uniqueness of our own solar system. Oops. And it didn't just find one multi-planet system, so this is actually slightly older orrery. So we have the solar system here on the left, and they show all the planets that Kepler discovered here that orbit with a system with more than 1 planet around its star. So you can see this whole wealth of planets, and most of them are smaller than our solar system's orbit, right? Most of them would fit within the orbit of Venus. Some might just about be on the orbit of Earth, but this is very, very different from what we expected to see when we started looking for these planets. So now we found these planets. We want to know, what are they made of? Are they, right? What is their atmospheric composition? Can we learn a bit more about how they formed? So how do we now find the exoplanet atmosphere, right? How do we do the next step to actually get some more information on the planet's properties itself? Well, in the solar system it will be easy, right? We can show this picture at the start, where during the Venus transit, we see light from the sun filtering through the atmosphere. We can directly measure the properties from this. We can observe it. We have space station around Earth, so we can take pictures of the thin sliver of the Earth's atmosphere. We have probes on Mars that have taken images of the sunset on Mars. So we know exactly what it looks like. And we can tell detailed in situ measurements of the composition, variation pressure and everything, and temperature and everything else. But how do we do this for planets around other stars? Well, the first thing you need to know is that when we measure the properties of the atmosphere, we're averaging over the entire planet, right? We're not just looking at a small region, we're looking at the average of the entire planet. So necessarily, our observations won't be as detailed as what we can get for anything in our solar system, even when we use telescopes to just measure from Earth the properties of their atmosphere. So let's start with the simplest case, where we can separate the light from the planet from the light from the star. And now we can use an instrument like the spectrograph to again separate the light over the multi-wavelengths and multiple colors and try to learn a bit of, look for those unique fingerprints of atoms and molecules. And so here, this rectangle is already observed, this particular star and or planet. And what they found was this here. And you see there's a bit of a dip here in light, which is due to water in the planet's atmosphere. Here on the right, we see signals from carbon monoxide and methane. And so we can learn a bit about the composition. But again, this is only possible for these planets because we can see the light separate from the star. The interesting thing is, if we can separate the light from the planet and the star directly, we might even be able to measure their rotation period. So how does that work? Well, imagine we're looking at a planet here. It looks very boring, but this planet is rotating around its axis. So it has a day, right, on the planet, means that you rotate 360 degrees around. This looks very boring, but if we turn on our radial velocity measure to basically looking for the shift in light as it rotates, we know that here on the left, the planet is that side of the planet is coming towards us, and here on the right, that side of the planet is moving away from us. So let's color code that. So on the left, we have light that's blue shifted, and on the right, we have light that's red shifted. So if we now look at just a small region of this planet where the light is blue shifted, and we look at the brightness from that molecule or atom that we're looking at as a function of its velocity here on the x-axis, we see that it's maybe not that bright because it's a small region, but we see that this light here from the left edge that's coming towards us is blue shifted. If we look at light here in the middle, that light is basically coming from a region of the planet where it's not coming towards us nor moving away from us, so it appears exactly where you expect it to be. And then if you move to the right side, the light is now moving away from us, so it's red shifted. If we now sum up all the light over the entire planet, what we see, rather than these very narrow peaks that may look a bit like this, right, that are very narrow, we see a line that is much, much wider, right? It covers much, much more area because we see light coming from parts that are moving towards us, parts of the planet that are moving away from us. And so we see a much broader profile, right? It looks like it's moving like that. So if we now observe that, this was done by Professor Snellen from Leiden. They observed this planet here called Beta Pictoris b. And what they did is they observed it with their spectrograph. They're looking at carbon monoxide. And this is the line they measure for carbon monoxide. So in itself, this doesn't look anything special. We know that the peak here is somewhere around here. The planet is moving away from us by about 17 or 18 kilometers per second. So it's on its orbit. It's orbiting at quite a high velocity. But we also know that this line here has a width of roughly 50 odd kilometers per second, right? So it's quite broad. If we now show what you would expect if the planet was not rotating, you would expect that the CO signal would look something like this, much, much narrower. And when we work this out, what you find is that Beta Pictoris b is rotating around its axis with a velocity at the equator of about 25 kilometers per second, which means it's rotating much faster than Jupiter and Saturn, and that we actually know that its day will be shorter than a day on Jupiter, right? Shorter than about the 10 hours that Jupiter takes to go around its axis once. So that's one of the cool finds you can do with these young planets. But unfortunately, it doesn't help us in most cases. Most planets we know are not directly imaged. They're seen, discovered through the radial velocity wobble and the transit method. And so can we learn something about their atmospheres? And the answer is yes, we can. So if I draw a schematic of what the planet looks like when it orbits its star, we have the transit here. So this is when the planet passes between us and the star. And in this case, the light from the star will filter through the planet's atmosphere on its way towards Earth and gets imprinted with the signal of anything that's in the atmosphere. Then as the planet goes around its orbit, we basically see the brightness change. That's sort of shown here in the bottom, because we see more and more of the day side of the planet, right? We can see as it goes along the orbit, we see more of the day side until about half an orbit later, we have something known as a secondary eclipse, where the planet passes behind the star and the light from the planet is blocked. So we can use that to measure light from the planet. And then finally, we have here called the phase curve, which is basically the phase variation, just like we see with the moon, right, or Venus, where we see different amounts of illumination on the day side of the moon / Venus as directed towards Earth. So I'm going to do a short demonstration of how we can use this transit to measure some signatures. So I showed this spectrum from the sun here on the right earlier. I told you it was taken with my spectrograph. And so this is the spectrograph here. Light comes in through an optical fiber here, gets reflected here by an off-axis parabola, which makes sure that the light is nice uniformed. It hits a grating, which then separates light into its different wavelengths. And then it goes through actually a normal camera lens onto my detector. And so what I have here, and I need to go to here and start the software. Okay, is, and I hope you can see it, a simple LED light source, which basically gives us sends light into the spectrograph. I have the fiber that goes into the spectrograph, and I'm just going to put it down because what I have here is a set of color fields. So I have blue, green, yellow, orange, and red, as well as two other filters. I've got a light pollution filter or ultra high contrast filter, which you can see here. It looks a bit purplish when you look through it. And I've got a solar continuum filter, which will look very greenish if you look through it. So you should be able to see it here. And now what I'm showing here is sort of what the light at the moment, what you're seeing is a spectrum of the LED without any filter in place. And here on the right is roughly orange light, orange reddish here on the right. And on the left, we have basically bluish, and in the middle, it's greenish, roughly. So if I now pick a filter, and I'll just show you what it is, if you can see this. So this is a green filter, and put it in front of the detector. There we go. We see that it blocks most of the light, blue light. It lets through the green light, and then starts blocking a bit more of the yellow and orangey light. And basically, if you had a larger detector, you would see that basically red light is completely blocked. So if I now pick a different filter, I want you to say what you think the color of the filter is that I'm using. So I'll put this in here. So any guess what kind of filter this is? Okay, see red. Well, it's quite close to red. It actually turns out that this is the orange filter. And that's sort of the same color as the street lights, you know, the orange street light with sodium. They have sort of a similar color as this. So let me pick another filter here. So what do you think this color is? See blue? Yes.
Red.
It is a bluish filter, so you can see that it blocks basically almost all the yellow, red, orange, and most of the green light, and then it lets through some blue light. And so now I'll pick one more filter. I think this is quite a nice one. So here it goes again. So what do you think this is? Okay, that's pollution. I see sky pollution. Yes. So this is a filter. You can also see that's much better quality than the square acrylic filter used before. It lets through much more of the light. And it also has a much nicer shape with very sharp edges. But the main thing is it blocks here this red part here, or red-orange part here on the right, where the sodium streetlights and the mercury streetlights emit a lot of light, but does let through a lot of things that you would see in nebulae as well. And I'll show you one more thing because you can actually see an interesting effect here. This is the solar continuum filter. And this filter works with something called interference. So basically, it only lets light through of specific wavelengths because it sort of bounces back and forth in the filter. But if you tilt the filter, so as I'm doing now, you can see that the wavelength changes because the distance that the light bounces in the filter, it gets larger. And so different wavelengths gets through. So this is what it should look like. And if you tilt it by about 45 degrees, you can tune this filter. And I don't know if you have an H-alpha telescope, if ever used one. It uses some very similar technique. They basically tilt effectively the filter in between to change the wavelength, so you can look at different parts of the H-alpha line and the different parts of parts in the solar atmosphere. Okay, so I'll just close this down, and then we go back. So how does this help us? Well, these filters basically block specific parts of the wavelength and let through other parts. And so as they do that, if we look at a planet, it doesn't have the glass filters, but it does have atoms and molecules in the atmosphere. So if we look at one wavelength where the atmosphere is transparent, so for instance, if we go on Earth, it's not quite transparent, but at red wavelengths, we know at the sunset looks red because all the blue light gets scattered away, but the red light basically passes through the atmosphere almost unhindered. It basically passes very close here to the surface of the Earth, or the planet we're looking at. And then we measure a size that's roughly like this. Remember, the depth of the transit is directly related to the size of the planet compared to the size of the star. But if you now look at a different wavelength, let's look at blue light, for instance, for the Earth, or maybe at the specific oxygen wavelengths in the Earth's atmosphere that get absorbed. The light comes in, gets either absorbed here, or maybe scattered in any random direction, but is basically lost. And the atmosphere now appears much bigger. It just absorbs much, much more light, and we get a deeper transit, right? The planet appears bigger because the light doesn't get through. And this is why if you look at the Earth's atmosphere, it would look quite reddish if you're able to see it from a distance, right? The red light gets through it, the blue light gets scattered. So if we look at the starlight being absorbed, the sunlight in the Earth's case, the blue light gets absorbed, the red light gets through almost unhindered. So the atmosphere would look a bit like a reddish haze. So, or the sunset, if you would imagine that as well. So if we now compare the two, right, imagine light gray is the light just passing through unhindered, or red light The black is the blue light that gets scattered by the Earth's atmosphere. We see that the Earth would have a deeper transit in blue than in red. Of course, this is exaggerated. In reality, for the Earth, the increase, even the strongest increase, is less than 1% of the transit depth, right? And the transit depth is only 1% of 1%. So that's a tiny, tiny increase. But the principle still works, right? This is just a bit exaggerated for illustrative purposes. So let's look at some real systems. I can't show a spectrum of an Earth-like planet just because they are too small to get any measurable signal. But if we look at some of these hot Jupiters, these planets like 51 Pegasi b, so the first planet that was discovered, but now one that transits, and this planet is called HD 189733b. Again, a very catchy name, but for astronomers, quite telling. What you see here is the light curve. So the brightness as a function of time. And you can see how well they measured that. And then it goes down. You have the trend. You see this bump here. This bump is actually not an error in the measurement. It's the planet passing over a star spot. So similar like the sunspot, the star has spots. And the planet just happened to cross one of those star spots, which gave us a small bump in the light curve here. And actually, this was 2 occasions to have a different star spot, which is in the black point. But if you do this at multiple wavelengths, what you can do is you can build up that measurement as a function of wavelength. How large does the planet look? And you get this diagram here. So on the left, they showed basically the size of the planet compared to the size of the star. And on the x-axis here is the wavelength. And basically blue is here. And red is on this side. And it goes all the way to the near infrared. And what you see here, these points with these error bars are actually the real data. You see that at blue wavelengths, the planet appears much bigger than here at the reddest wavelengths, right? There, it's almost 0.002, which for exoplanet people is actually quite a large increase, larger in the bluest wavelengths. And this means that blue light gets preferentially absorbed or scattered in the atmosphere. And so what people have done is they then calculated, well, if you could observe a sunset on this planet, what does it look like? Well, actually, it might look a little bit like what we would see on Earth. The star set, in this case, on this planet would look quite orangey. I should caution you, don't expect to see a star, go there to see a star set, because this planet is still well over 1,000 degrees, so a bit toasty. Even on its near the terminator where the sunset is visible. Of course, we haven't observed just one planet, we've observed multiple planets, and some planets look differently. And this data set here on the left looks very noisy, so don't worry about it. But the main takeaway is it has this very big peak here in the middle, and then it's sort of flat, and then a bit of an increase here on the right, on the left, which means it doesn't have as much scattering as the planet we just looked at, HD 189733b. And so using this data, people have been able to, again, predict what the star set would look like there. And it would look much, much different, right? Because the red light in this case gets absorbed, mainly by sodium in the planet's atmosphere. And so blue light might actually get through the atmosphere much better than red or orange light. So this might be what you would see if you would go there. Again, not a good holiday destination because this planet is, I think, about 500 or 600 degrees hotter than the other planet we looked at. And because it's so hot, when we've looked in the UV, what we found is that this planet actually has sort of a cometary tail of hydrogen gas being blown off by the stellar radiation and being dragged away. And so you see a big, if you look at them in the UV and you measure it, it looks like it has an elongated tail trailing behind it with hydrogen gas being lost from the atmosphere. So this planet is literally losing mass and effectively with time will shrink. But there's another cool thing we can do with these transiting planets. because as a planet goes around the star, it will move at a much faster pace than the star, right? If we look at the Earth and the sun is moving at 10 centimeters per second. Again, a speed on the order of this. But the Earth, and you probably are not aware of it at the moment, right? Because, well, we're sitting here, we're moving at about 30 kilometers per second along our orbit. So we're moving much faster than the sun. So any signal from water or other molecules in the Earth's atmosphere will be shifted by quite a large amount over time. If we go to these whole Jupiters, the star might be moving at 100 meters per second, but the planet might be going at over 200 kilometers per second. So that's almost 1,000th of the speed of light. And so what we can do is we can try to look for these signals. And this is a signal from water, where we're looking at, this is just a model, and this is just to show what you expect. So on the x-axis, I show the velocity. On the y-axis, basically, we call it orbital phase, but time. And the transit starts here, ends here. And so we see the planet's absorption starts blue shift, and as it goes along, it becomes red shift. And this planet moves at about 200 kilometers per second in its orbit. And we only see a small part of it, but we see it shift by 70 kilometers per second on either side. So that's a nice difference. And this was our prediction, what we would see. This is what we saw. And unfortunately, we didn't see any clear signal. And if you compare the results along this, yeah, the black is the real data. The gray here is what we expected. And we didn't see any water on this particular planet, unfortunately. But we can show that this would work. And we can use this to find atmospheric signals as well. I mentioned briefly secondary eclipses. In this case, we're looking at the planet passing behind the star. So here on this side, we see star plus planet at the start and end. In the middle, we just see the star. And at the end, we see star and planet again. So if we take the difference, what we get is that this amount here is just the light from the planet. In this case, it's about 0.1%, so 1 part in 1,000. And we can calculate the temperature of this particular planet, and it's over 3,000 degrees. So this particular planet is as hot as some of the red dwarfs we can see in the night sky. So that's sort of a very extreme world, but gives us useful information. Interesting thing is, if you observe these more and more, this is a particular planet called WASP-12b. We observed it twice, once with the INT, once with the Liverpool telescope. And you can see in the dashed line here is what we measured for the Liverpool telescope, in the solid line with the INT. And here it's resolved, the reverse. So the dashed line is the INT. And you can see this big difference. What does this mean? Well, this means that the planet was almost half as bright when we observed with the Liverpool than when we observed it with the INT. And that means that its temperature may have changed by 500 degrees. And we might be looking at storms on this particular planet, right? So this is really interesting because we might be looking at weather at other planets. Final method is looking at the phase curve. So I measured that as the planet goes around its star, we have the transit when it blocks a bit of the light, but we're looking at the night side of the planet. But as it goes on in its orbit, we see more and more of the day side appear into view, and you might just about start to see it. It's hard to see, but as it goes about a quarter of an orbit after the transit, you can clearly see that the day side appears, and that adds more and more light to the system. So we can use this to find, measure the light coming from the planet and learn more about this. And this is similar to what Galileo observed for Venus. So this is his illustration of Venus, where you see when Venus is close to the Earth, you see just a small sickle with almost nothing else. And when it's on the other side of the sun, it looks like a nice full sphere. So we have that same thing with exoplanets, where during transit, we just look at the night side, it's the dark side. And then half an orbit later, we look at the day side. So we can look for these variations in brightness and use this to infer, for instance, temperature distribution about a planet's atmosphere. So this is just a very simple model. We see that here this brightest point is the hottest point on the planet. It's not exactly when the star is straight overhead, which is here. This is where the star is straight overhead, but a little bit offset towards the afternoon. Just like on Earth, the afternoons on this planet are warmer than the mornings. We've done this with the Kepler Space Telescope because it observed for so long. We could see these nice variations. So here you see an example. And now look at the scale. These are called ppm, which is parts per million. So this is about 50,000 times fainter than the signal from the star. So this is a tiny signal. And we've managed that as well for a planet that's about, I think, about twice the size of the Earth, which goes around its star in about 20 hours. And we measure a temperature that's larger than 2,700 degrees. So this is a really, really hot and toasty planet, but it's likely rocky. Well, rocky for a given value of rock. It might be actually a magma world, just completely covered in magma, just because it's so close to the star, it gets so hot. If you observe a lot of them, you start seeing weird things. You might see that it's not the brightest here right when we see the full day side, but a bit earlier, or in this case, a bit later. And this tells us something as well. So just as I mentioned on Earth, the hottest point is not when the sun is straight overhead, but typically a little bit later, an hour or two later. That's because the atmosphere and everything is sort of a heat capacity. It holds on to the heat for a while before, so the heat keeps heating up. And the same happens on these planets. And so what we think in the one case, we're looking at sort of the hottest point being the afternoon. And so the hot point, we're looking here at the afternoon side. The blue indicates when the star is straight overhead for the planet. And so it's going around in this direction. And so we see this brightest peak before the eclipse. So basically before we see the full disk. For cooler planets, what we might be looking at is clouds. And clouds can form on the cool night side, get blown around, because these planets might have winds up to 10 kilometers per second, might blow around to the day side where they start to evaporate. So then we expect that the morning will be nice and cloudy and we get a lot of reflected light, but over time those clouds basically evaporate, disappear, and they may have semi-clear afternoons. And so if we can observe this, we might be able to give a weather forecast for these planets. Of course, it's more complicated. So we observed one planet where the brightest point might shift between the morning and the afternoon side, which could be things like on sometimes it's nice and hot, right? So it's a hot afternoon, but sometimes it cools down enough, the clouds form on the night side, they get transported to the day side. So we might see a variation in that. That would actually tell us that there's weather on these planets as well. And so I'm very conscious of the time, so I'll just do a very quick summary thing is that we're not just looking for these atmospheres, we're also looking for things like exorings, exomoons, and even exocomets. And just to set the context, if we look at the planets in our solar system, especially the giant planets, all of them have rings. So we have Jupiter here, they have very thin rings. Saturn, of course, everyone knows for the rings. But Uranus and Neptune have clear rings as well. So they seem to be ubiquitous in the solar system. But are they out there as well? Well, one object called J1407b, they observed it with SuperWASP. And so you see this light, and this is not noise. These are just observations taken night by night. You see this huge dip where the star almost disappears. This is basically, there's no star visible. This is its normal level. And you can see this huge dip here that lasts almost 40 days. And that dip is associated with rings. And not just that, I showed this here. If you zoom in, you see that those things are actually just kinks and wiggles. And these are basically rings where you just get a bit more of your ring crossing a star. Or here there's a ring that's moving on the star, and then another ring is moving away, so it gets brighter again. And you can see all these things. And if you make a model, this is an artist's impression. This object is huge. This diameter is about 90 million kilometers up to 100 million kilometers. So almost it would fit roughly between the Earth and the Sun, right? It would touch the Earth and touch the Sun almost. This is Saturn for comparison. And someone had fun trying to imagine what would it look like from Earth if we replace Saturn by this object. It would be much brighter and much larger than the full moon, which you can just about see here. Right, that's the moon. And that's what it would look like if you would replace Saturn by this giant ring system. It would ruin nighttime astronomy because all night would look like the video I had in the beginning, or at least half the year. But it would be a really impressive sight to see. And then at the end, I want to show that we're not just finding planets, we're actually finding comets as well. So we know comets have tails and a coma, and so you see a very sharp increase here, and then a long tail here on the right when the tail is moving across and moving off the star. And so this is a signal of a comet around a very young star, and these comets are nothing like our own. These comets may be, what is it? Well, have comas that are hundreds of thousands, 100,000 or more kilometers in size. So these are giant comets from a young star, but nevertheless, we're starting to find these comets around other stars as well. And we actually know that these comets have a lot of calcium in it. And then what's the future? Well, we're building ever bigger telescopes, so we might start to observe the atmosphere of an Earth-like planet in the next decade. We might even be able to find oxygen if we find a suitable target. And the European Extremely Large Telescope shown here, which will have a diameter of 38 meters, will be a huge, big step to getting us to that stage. And with that, I would like to thank you, and I'm happy to answer any questions you have.
Ernest, thank you very much for a thoroughly entertaining and informative talk. And I especially enjoyed your demonstrations as well. Right, ladies and gentlemen, it's question time. As normal, I'd prefer a digital hand. Otherwise, shake a fist at me, try and draw my attention, and we'll get you to unmute your microphone. Whilst everybody else is thinking, Ernst, do you have to take into account the interstellar medium when you're taking your spectra?
Well, a little bit. You have to be a bit careful. But as I said, if we take our spectra, we typically take a spectrum when we just see the star, and then when the planet, or sorry, on this side, the planet moves in front. So the interstellar medium would be visible when we just see the star. That would always be there. But we only see that we're looking for the variation. So the planet now is in front. We see the light from the star, well, filtering through the planet's atmosphere. And then again, we just see the star. So if we compare very carefully the interstellar medium, we can remove that more or less.
Okay, thank you for that. So over to you, ladies and gents. And Peter Jarowski.
Fascinating lecture, Ernest. I used to be involved with the radial velocity technique in detection of exoplanets, so I've got a few in my bag, but that was quite a while ago. And one thing I've not actually kept in touch much with this field was the concept of exomoons and exocomets. Is there any evidence of any exomoons?
We're looking, but there's one tentative candidate, although there's been debates in whether it's a real detection or not.
Yeah.
So, well, if you look at the Galilean moons, for instance, for Jupiter, they're tiny compared to Jupiter itself, right? They're roughly a bit larger than the moon, but not much. So if Jupiter covers 1%, the Earth covers 0.01%, these moons cover, again, a factor of 10 less. So they're tiny signals you may be looking for, which might make it harder to find. But people are actively looking. So
Yeah.
there is a whole, yes.
And with improved instruments, obviously, the results will come quite quickly, I suppose.
Well, that's what we hope. So,
Yeah.
yeah.
Thank you very much. Thanks.
Okay, Peter. Nick Nichols.
What are the latest ideas about what's orbiting Tabby's star?
So I haven't actually been catching up for the very latest on Boyajian star, but what we've seen so far, it looks like it may be either a planet being ripped apart, or that has been ripped apart, or maybe had collided with another planet, and sort of the dust clouds that are left over, they will spread along the orbit. And so they might be the things that are going around. That was one idea. The other thing, when people are looking at it, is I think a very peculiar nature of the star. And don't quote me on the exact details, but I think you can get sort of either dust forming or something happening on the surface of the star that basically causes dips in the light that are not periodic, but do happen. And I think they've seen some weird spectral changes that are associated with that type of star. But yeah, I haven't been keeping up to date on that one.
Okay, Michael. And we've got a question, a question from Lee Cooper. The very large exo rings, surely they cannot be stable for long. How common
do these seem to be? So the stability has been an issue. So people have been looking to see if that thing repeats. So Matt Kenworth in Leiden has been leading that. And the original prediction was based on their velocity, it should have repeated, I think 4 or 5 years ago. And we still haven't seen anything. And this would be very obvious, right? It dipped by 100% over 20 days. So you would see that if it's in the data. And we haven't seen anything. So people start working, okay, it might be on an eccentric orbit, because then it means that it passed during periastron. So when it's close to the star, it's moving really fast. And then it slows down when it moves away and spends quite a long time away and then comes in again. But every time you then pass the star, you might disrupt the rings, unless you might have some moons there, or a very particular, I can't remember if the direction is, you need to rotate the rings, I think in this opposite direction to the orbit, if I remember correctly. They can make them stable for longer. So we're still not sure if that's an object that actually is a planet orbiting the star, or if that's just happened to be a rogue planet effectively with a disk that just passed along the line of sight, so somewhere between us and the star. We know the star that we're looking at is young for that particular star system. And so it would have been at an age where there could still be planets with disks around them. But it could also be one of the planets that formed in that at the same time as the star, because a lot of stars typically form at the same time, that just moved around and just happened to pass. Although it's very unlikely, but we haven't been able to solve that mystery there. We have some other candidates where we see similar things, but so far none of them have repeated, which makes it hard to say whether it's a real thing, or in terms of that it's a nice planet that's bound and does it periodically, and also how frequent they are. But yeah, we're looking, and we found, for instance, if I remember correctly, Fomalhaut, one of the other stars have pictures taken directly. We see a lot of reflected light, which could indicate that it's sort of a big disk around the planet, a smaller planet with a big disk around that reflects light. But again, there's a lot of circumstantial evidence that rings are quite common, but we haven't seen a good enough data set to say, yes, they are there. So one of the things I'm looking for is, how can we spot these rings more efficiently?
Okay, thank you.
Paul?
Yes.
Ernst, you're showing us some data from Super WASP and the Liverpool telescope, inferring that the surface temperature of the object under observation had dropped by 500 degrees.
Yes.
Over what time period was that?
That was over a year. So the two observations were separated by a year. So what we've done now, and we're still working on it, my PhD students work on that. We've gotten observations over, well, now 2 years, where we observed it for typically 1 or 2 nights, then a gap of a month, and then another 2 nights to hopefully see if it's on shorter time scales. And most recently, we had a look with the data from the TESS satellite. And there, over the course of 28 days, we didn't see any significant difference. But again, if these are weather, it could be, yeah, we could be unlucky that we just had the period where it was nice and stable weather on the planet, or rather than the storm. So we're not exactly sure. The timescales we would expect are pretty order of months. So the other stars showed had P7 seemed to vary on the order of a month or so.
Yeah, it seems that 500 degrees temperature difference is a substantial change of energy as well. So like the thermal inertia of the system would have to be quite dynamic.
Yeah, so it's not that bad, because if you form cloud fronts on the night side, you can cool quite effectively on the night side. And you might have sort of a feedback effect where you cool down a little bit. You form clouds on the night side, get a little bit more on the day side, that then cool down the day side more rapidly. And then you get sort of a feedback loop, because the day side is now a bit cooler, the night side get cooler still, so more clouds can form. And you can get feedback loops like that. So there is several mechanisms we can get quite a rapid change in that sense.
Okay, thank you.
Okay, ladies and gentlemen, I think it's time that we thank Ernst for an excellent evening of talks and demonstrations, and we've worked him really hard with the questions as well. So can we give a big Mexican Swinton Astronomical Society thank you to Ernst? Thank you very much, sir.
You're welcome. Happy to do it.